basically my PhD topic is on the spatial modeling of transport infrastructures in the context of energy decarbonization, energy system decarbonization. But in the first 2 years, so I'm in my third year now, in total, my PhD takes 4 years. As I'm halfway through, I focused on charging infrastructure allocation. And so today I will talk about this and also scratch upon a little bit on the surface of spatial modeling. I will not go so much into detail with formulas and equations, but somehow mention how the conceptualization looks like behind the spatial modeling and what is interesting in my research specifically. Just a short introduction of my research team in Vienna. So this is the whole, or mostly most of my team, and this is my direct office, or the people that I'm always discussing or have been discussing my research with. So some of you may already know Hans and Sebastian. Sebastian was also here last year for 3 years and is also collaborating with NTNU researchers. And same goes for Hans. And we will also hopefully collaborate with me long term. So I'm looking forward to this. But also an honorary mention to Theresia. She's not anymore part of our team, but she was 2 years with me in the team, and she's already finished, but I just want to mention her because she was also very much involved in my research and discussions and also in writing my papers. And yeah, and Marcus is a student assistant. Yeah, so there are two main motivations behind my research topic. So one is that charging infrastructure is, of course, both a motivator and a barrier to the electrification in the transport sector. And the other one is more related to the spatial modeling aspect. So if we are talking about or planning pathways for energy system decarbonization, then we're doing this large scale in energy system models that are more, when we're talking about spatial granularity, here we're more in on like continent or country level. And if we're talking about charging infrastructure allocation, we're really going down to like kilometer, meter spatial resolution. And just a short introduction to the NUTS classification. So this is a nomenclature which is used on for data sets. First and foremost, if we classify the spatial resolution of data sets, we have NUTS 0, 1, 2, 3. So here you see an illustration that kind of shows what the resolution is. NUTS 2 is country level, and then we go down up until municipality, and it is this classification is essentially classifying regions within Europe and based on socioeconomic parameters, and it is widely used for data aggregation first and foremost. And so I'm gonna mention this a lot multiple times throughout the presentation. So it goes down until municipality level. And so basically in the energy system, in like large scale energy systems, we have a more simplified representation of the different demand sectors, right? So we cannot go into all the details of all agents, but we need to know which parameters are actually relevant in order to not underestimate or overestimate plant capacities and energy demand. And what's interesting here is definitely in terms of charging infrastructure allocation, which parameters are actually relevant then in terms of spatial resolution also to the energy system modeling. And this also varies from spatial resolution. So that's the context of my work. And basically, when we're talking about charging infrastructure allocation, this is influenced by two major components in the system. So one is the energy supply infrastructure, which dictates the installation costs, or depending where I install it, I have different connection costs to the grid or different supply costs. And also this limits the capacities that I can install. So how many charging stations can I connect, etc. So this is the spatial aspect that is important here. And then we also have on the other side where I put my charging station. This is influenced by the transport sector. So where are where are vehicles charging and what are their mobility patterns, what are the seasonal differences. And then on the other side, we also have different consumer groups. So we have passenger cars, we have trucks, we have also different requirements for charging speed, for driving range, also depending on what good I'm transporting. And then in terms of long-term planning, it's also interesting that, of course, the timing of the electrification happens at different times for passenger cars versus, for example, trucking. Yeah, so this is the whole context of it. And then I also have the transport infrastructure, which also dictates, of course, where the vehicles are driving, and also allow us a certain shift to other modes. Yeah, so up until now that I have been focusing on charging infrastructure allocation at a very high resolution. So what we had was a highway network and also small scale. So only for Austria, along the highway network in Austria, and it was really service area level to decide at which charging station to place how many charging stations and what capacity is needed. And then I have, of course, the information on the one side from what are my installation costs that I can include specifically for each service area, and the limitations on local capacities. And this was just highway charging, so just for long distance driving. And focusing on the passenger sector, also including seasonal variations, and just for one specific point in time. And within my work here, we extended the horizon together with Stefan, and Jonas was also involved in extending it in the sense of that we're not only looking on passenger cars, because it's quite obvious that passenger cars will be mostly electrified. That's what the trend is currently. And for freight, it's not so obvious. That's why it is interesting to look at it also long term, and to not only include electrification as an option, but also different fuel choices such as hydrogen. And to also include the aspect of transport infrastructure. So now with this wider scope, we also try to do this not only for one country, but also go beyond the borders and do this large scale, which also needs a more efficient model. So I just want to shortly illustrate how we're going from like super small scale, so like high granular spatial resolution, where we really plan for each service area charging stations with their capacity, which is then which allows us to really include the local constraints, such as also space restrictions and how many charging stations can be involved, etc. But this is formulated as mixed integer linear program, which is very difficult to scale up for whole of Europe. And then also the question arises if it's needed to plan for each service area, or is it actually more efficient to plan it large scale and to then downscale the results on a larger scale. So with the next model concept that was here also further developed, we're including not only one mode, but the idea is to include multiple modes. This is just an illustrative image, so there are also road connections between Munich and Regensburg. But the idea, or what this illustration tries to convey, or is hopefully conveying, is that we try to include multiple different transport infrastructures, so not only road anymore, but also flight connections, waterways, rail connections. So this is the basic concept and the idea to implement, right? And then we go up from service area granularity to accumulating the required charging or fueling capacities to the edges. The nodes here represent the NUTS 2 regions, which I talked about earlier. So, for example, NUTS 2 region here in Norway is Tondelag. I'm not sure if I'm spelling it correctly, but this, for example, and we have one big city, which is Trondheim. So this is essentially what your Salzburg and orange region is indicating. And so we go up in spatial resolution, and we're simplifying the deployment of charging infrastructure in the spatial dimension. And we also try to, but also consider different product groups, now focusing on the on long-term planning for trucking decarbonization. And this is formulated as a linear program, and which allows it to scale it up, so to apply it large scale, and to also in terms of, because we're planning long term, so we need to also include some uncertainties on future fuel prices, or also future how the energy supply infrastructure will develop locally. Yeah, so the basic, there's the case study is large scale. We're not doing whole of Europe, but there is the so-called Trans-European Transport Network, which is a concept by the European Commission to connect all different regions of Europe via viable transport infrastructure. And this transport infrastructure not only includes road, but also rail, ports, and also airports. And there are different corridors, which are the different colors here. And we're focusing on the Scandinavian Mediterranean corridor, which is from Italy going up to the north of Norway, so the pink one. I hope you can recognize this. And this is mainly road infrastructure, but also rail. So we have those two modes in this case study. And currently the goal is to have until 2035, each 120 kilometers, one charging, at least a charging station for trucking, and then each 200 kilometers hydrogen refueling stations. And this is quite interesting also, this case study, and focusing on road for now, and not extending it to all of the modes, because we're focusing also on the technology shift here. So when is this technology shift from diesel to electrification happening? Or is it happening in the direction of hydrogen fuel cell vehicles? And this is specifically an interesting point, because there are also different or quite uncertain projections concerning this technological shift, and specifically hydrogen fuel cell trucks. So how many will there be, and will there be any, or what is the application, in which applications do we need them, as they are quite diverging also, not opinions, but research results and projections for the upcoming years until 2050. So some may argue that it's a niche application, so battery electric vehicles versus fuel cell. The obvious trade-off is charging speed and driving range. And then there are also, for example, the European hydrogen backbone is planned based on the assumption that until 2050 we have 55% of hydrogen fueled trucking. And so this is the range of what we're talking about, that this is uncertain, and also a motivator for this work. Yeah, I won't go into the details of the analysis, but just mention the most important or the interesting drivers that will be relevant to this analysis. On the one side, I want to mention the modal shift. So we're considering trucking and rail. We're basically focusing on trucking and what the fuel mix will develop here, but we're also including rail as an option to shift to. Because it's also one of the core goals of the European Commission to increase rail freight, or double the rail freight that is happening today until 2050, which is interesting, definitely in terms of infrastructure investments, as these are quite costly. And such a mode shift is, of course, also motivated by transport costs. So what you see in this curve here, is that at certain distances, different modes are the cheapest. So normally always the cheapest would be chosen, and at certain distances you have a break-even point. So for example, between road and rail, which are dictated by the terminal cost. So how much does it cost to put 1 ton of product onto the vehicle, which is the most costly with maritime and the cheapest with road, so with trucks. And this break-even distance between road and rail is at about 500 kilometers. So we're also considering the different routes that are within this whole extension of the corridor. So it will be also interesting how this will shift for different routes to and product groups to rail or not to rail. And also this green line here, the cost curve of road, will be also impacted with time and different in time based on which technology we're looking at. So is it battery electric vehicle or hydrogen fuel cell or fossil fuel? So the break-even point would also shift. And then again, that question will also back because with battery electric vehicles and the extra needed charging time, this will also have an influence on the transport costs or even limit certain goods to be transported with battery electric vehicles. So there might be also a choice towards hydrogen fuel cell vehicles versus costly rail, for example. And then we're also considering different hydrogen supply options. So either hydrogen can be produced on site via renewables that are present on site, or most likely via the connection to the power grid, or it can be delivered while produced being centralized production. So either via pipeline or trucking. And this also, the interesting thing here is that then the fuel price also depends on how it is delivered. If it is produced on site by being connected to the power grid, the price will be dependent on the electricity price. And if it is a centralized production, then it will be dependent on the current hydrogen market price. And and this is also expected to be different in different regions here, these transport costs, because the extent of our case study is quite huge. And so here it is expected that there will be also eventually hydrogen production points. There will be hydrogen production, and the transport costs would be here then lower than in the Austrian Alps. Yeah, so based on this, we outlined what our collaboration will focus on, and also this kind of reflects how the paper is structured. Also in some way goals always to publish at some point, right? And so the main research questions here are, on the one side, what will be the investments for charging and fueling infrastructure needed along this corridor, and then also if the fuel mix and the technology mix along this corridor will be long-term affected by the development of energy supply infrastructure, such as the power grid or also the hydrogen backbone. And so can this actually induce some kind of usage or application even of hydrogen backbone? And basically, this will be one of the first approaches to also plan multiple or plan charging, fueling infrastructure for multiple fuels and technologies. And then again, we will also not plan it in such a granular way that is typically done for charging infrastructure, but also scale up, so that's two-level. And the long-term planning aspect with taking uncertainties into account is also some kind of contribution to the state-of-the-art. And we're generally looking at if there will be any geographic differences like we would expect based on the arguments before. And if taking into account energy supply infrastructure costs have any, or the connection costs to the energy supply, if they have any indication or any effect even on the fuel mix in the transport sector along this corridor. And then also we will take a look at if the geographic scale has an impact by considering not the highly granular resolution of maybe also NUTS 3 or kilometer, but NUTS 2. And and generally also what will be interesting is how the transport costs will develop in terms of how much does it cost to bring 1 ton of a product from A to B versus today. Yeah, so long term, we want to expand it also not, of course, only stick it to road and rail, but also expand it to the other modes, which is definitely a challenging aspect. As each of these subsectors are dictated by different cost drivers, but are also different in how the costs come together and what constraints are there between them. So this also takes a lot of expert knowledge in integrating these different sectors. And then also, of course, to expand this in a larger scale if the model is formulated efficient enough. Yeah. So thank you so much for your attention. This was from my side, and I'm inviting you to also be critical on what I presented today, because I also want to have your opinion on this, and I think this is the perfect frame to have new impulses and get new ideas. And yeah, thank you so much for your attention. Yes, intensely.